Hello everyone, my name is Jiddan, and in this video, I'm going to explore the use of the RefProp program or the MINIREFPROP program in order to help us solve thermodynamic cycle problems. And for example, in this one, in a refrigeration cycle, specifically a vapor compression refrigeration cycle, using an example taken from the Thermodynamics by Yunus A. Tengel. So in this problem, it is said that a vapor compression refrigeration cycle using the substance refrigerant 134A as the working fluid is used to maintain a space at minus 13 degrees Celsius to reject ambient air at 27 degrees Celsius. So the given values is that the compressor pressure is 100 kilopascals and the temperature at the compressor is superheated by the saturated temperature plus 6.4 degrees Celsius at a rate of mass flow of 0.05 kilograms per second. And the isentropic efficiency of the compressor is 85%, while the outlet temperature of the condenser is 39.4 degrees Celsius as a saturated liquid. So the problem asks us to determine the rate of cooling provided, the COP of the system, the exergy destruction in each component, the minimum power input, and the second law efficiency of the cycle, as well as the rate of total exergy destruction. Normally, solving these kind of problems, we just take specific or notable points in the cycle, in the vapor compression refrigeration cycle, and using the thermodynamics tables by comparing the enthalpies at specific pressures and temperatures using the saturated refrigerant 134A tables to find the values that are asked. But in this case, the RefProp program can be used to find these values faster and more accurately at the cost of not having some ideal assumptions to help us in solving the problem. And in the end, we're going to compare the value that we get by using RefProp with the values that we can normally get by using the tables and our typical assumptions. However, for this specific case, we're going to stop at part A, which is the cooling rate and the COP, as well as part C, which is the minimum input power, as well as the second law efficiency of the cycle, since the exergy and the exergy destruction for each component and the total exergy destruction is generally not directly accessible from RefProp, which doesn't have an inbuilt exergy component when we use the default tables, although we can also include exergy in the tables if we do some other manipulations to the options. Here we can use the MINIREFPROP program to help us find the values of the variables at each point of the vapor refrigeration cycle to help us solve the problem. So first we need to make sure that the substance we are using is already correct. In this case, we use substance and pure fluid and we select refrigerant 134A. But in this case, we're already on the right fluid, so we don't need to reselect it. And next, we need to open the TS diagram of the substance. So here we can see what the starting values are and the parameters for the temperature versus entropy plot. In this case, we can see that the pressure that is being marked on the entropy temperature versus entropy plot is from 0.5 to 9. However, as we see in the problem, we are starting with a pressure of 100 kilopascals, which is 0.1 megapascals. So we don't need to go from 0.5. And then the pressure that we are likely to go up from 0.1 is probably not as high as 9 megapascals inside the refrigeration system. So let's put a rough estimate of 1.5. And since we are working from 0.1 to 1.5, we can reduce the step value to 0.1. For the axis scaling, for the temperature, we are given that lower temperature is from minus 13, which is the temperature of refrigeration that we are expected to keep. So we don't need to go from minus 100. We can reduce this to around minus 30, while the upper limit of the temperature is at the evaporation of the refrigeration cycle, where it is probably not as high as 300 Celsius. We can reduce this to half, perhaps 150 Celsius. Keep in mind that these the access scaling values we can always change over time once the plot is already made. So now that we already have our plot, we can see that it's a little bit skewed to the right. So we can improve the view that we have by moving this minimum value of the plot more to the right as well. So in this case, we already have the temperature versus entropy plot of the refrigerant 134A, and now we can try to simulate how a typical vapor compression refrigeration cycle would look like. So we can use the starting values that we are given, where we know that the temperature at the beginning is 0.1 megapascals or 100 kilopascals. So we can open the modify plot tab and highlight this 0.1, and it will be marked by a thicker red line. And next, what we can do is that we know that the outlet of the condenser has a specific temperature, which is 39.4 degrees Celsius at a saturated liquid state. And how can we find out the exact point of this specific temperature? Is that we can first use the calculate function and use the saturation points at equilibrium, where we put in the temperature, which is 39.4 degrees Celsius, and we find out that the pressure at 39 degrees Celsius is actually 1 megapascal. So now we can actually highlight the 1 degree megapascal by using the modify plot once again. So this is the main two pressure lines for our system, and the other pressure lines we can just remove to improve our view. Now we only have our two main pressure lines for our problem. And so what a typical vapor compression refrigeration cycle looks like is that it would start at this point in the bottom right, but the problem states that we are starting at a superheated state from in the inlet of the compressor, so that it is likely to be somewhere higher up here, where the compressor would isentropically compress the refrigerant, raising it into a higher temperature directly above this point. After that, the condensation process at constant pressure occurs, where it will move up to the saturated liquid point on the left. And then the gas will be expanded in a flash chamber or in an expansion valve, where it will go back down and lose some of its temperature, where it will lastly be isothermally evaporated or heat rejection at constant pressure back to its starting point. And this is where the refrigeration effect or cooling effect occurs between the fourth point and the first point. And so what we can do to calculate the values that are being asked by our problem is to determine the enthalpies of the points that we are specified with. So first, we can already calculate the enthalpies that is given for the third point, which is over here. And we already did that by using the saturation points at equilibrium, where we find that the enthalpy, in this case, we know that the problem states at this point, the refrigerant is already at fully saturated liquid form. So we have a value of liquid enthalpy of 255.51 and the liquid entropy of 1.1877. And we can just add this label. So H3 is equal to 255.51. And we can just put this on the side for us to remember. And for the entropy for 0.3 is 1.1877. Next, we can find the enthalpy and the entropy values of the first point, which is the start of the compression point, which is likely to occur around here. First, we need to make sure to find out what is the temperature at the saturated point of this 0.1 megapascal pressure. To do so, we can use the same table, the saturation points at equilibrium, and we can just input the pressure of 0.1, and we can find that the temperature is minus 26.361 degrees Celsius. And the problem states that the temperature at the inlet of the compressor is 6.4 degrees superheated from the saturation temperature. So we just add 6.4 to this value, where we get around 19.939 degrees Celsius. However, we cannot just directly use this value for the saturation points or saturated vapor values, but we need to make sure that we are on the right point on this pressure line. And to do so, we can just use the shift button and just see on the top tab where we are probably at for this point, and we can use the specified state points to mark a certain point on this graph and find its temperature, pressure, density, enthalpy, and entropy. And so we can just zoom in on this section, and we just try to find a region where the temperature is, what is it before? Minus 19.939 or 94 as accurately as possible. I think this is a relatively good estimate, and we can just right click to mark this point, and on our specified state point table we can plug in the temperature of minus 939, and at this point the entropy is 1.768. And it would find the pressure values, density values, and the enthalpy values at this point. And we can compare that it is not much different from the values that we have here. So we can just use this as our working values. And we can reset back to our original view and plug in our labels. So for H1, we have 387.7, and for S1 we have 1.768. Now, as we have previously mentioned, from this starting point of point 1, it is isentropically compressed up directly up to point 2 if the compressor is 100% isentropic efficiency. However, the problem states the isentropic efficiency of the compressor is 85%, so that the actual point would be either more to the left or to the right of this directly above point. However, we don't need to find the exact point, but we can use the isentropic values to find the actual values. So we can find the isentropic enthalpy and isentropic entropy of this process at point 2 by using the same tables. So from our specified state points, we know that the entropy of the substance, the entropy of the substance stays the same over this entire process, but the temperature changes. And the pressure shifts from this point of 0.1 megapascals to 1 megapascal. So we can just plug in the values that we want from before, where the entropy is the same, but the pressure is 1 megapascal. And we get our other values where we find the enthalpy of this isentropic version of 0.2 to be 437.35. So H2S is equal to 437.35 and S2S is equal to 1.768. Same to S1. Using these values for H2S and H1, we can find the H2 actual that we can work with, where we can use the isentropic efficiency of the compressor, which is 0.85, and the formula of the isentropic efficiency, which is H2S minus H1 over the H2 actual minus H1. And we can isolate H2 actual to find that the actual enthalpy of 0.2 to be 446.11 kilojoules per kilogram. And so this is the value that we're going to be using to calculate. And lastly, we need to find the enthalpy and the entropy values for 0.4, which is likely to be over here. And lastly, for 0.4, based on the theory for the vapor compression cycle, between the outlet of the condenser and the inlet of the evaporator, it goes through an expansion valve, where the expansion process between 0.3 and 0.4 is supposed to be maintaining the enthalpy of the fluid so that the enthalpy does not change. So we can directly put in that the H4 is equal to H3, which is 255.51. However, the entropy will change as seen in the graph here, where it moves from top to bottom, and we can find the exact entropy by plugging it into the specified state points, where we know that the enthalpy is 255.51, but the pressure is going to the lower end of this graph, which is at 0.1. And so we can find that the entropy at 0.4 to be 1.2325 kilojoules per kilogram Kelvin. And so with these values, we can go to calculate the values that are being asked by the problem. And so given the values that we have already gotten from the MINIREFPROP program, we can use a spreadsheet to easily calculate the values that are being asked from the problem. And we can just plug in the values that are given from the problem and the values that we get from the RefProp program. So using the mass flow of 0.05 kilograms per second, the starting higher temperature, which is the temperature where the heat is being rejected to, which is the ambient temperature of 27 degrees Celsius, the lower temperature of minus 13 degrees Celsius, which is the refrigeration temperature. And the difference between these two, we can easily use a function to find out the difference. And so for convention purposes, and so that we prevent some negative numbers from appearing in places that we don't want, we can convert these two temperatures to the kelvins by adding 273 Kelvin, where this becomes 300, and the lower temperature becomes 260 Kelvin. And this is TH minus TL is the difference, so that it will stay the same. And we can just plug in the values that we have gotten from the program before. Keep in mind for H2, we use the H2 actual, not the H2 isentropic. And in this case, we haven't exactly found the entropy for 0.2 in the actual value. However, since we will see later that we will not be working with the entropy for this specific problem, for the specific things that are being asked, but it is also good to find the actual entropy later on. For S3, we can plug in the same values that we have gotten before. And then for the cooling rate, which is being asked in the first part of the problem, part A is the cooling rate and the COP. So the cooling rate, as we know in a refrigeration cycle, the cooling effect happens in the evaporator. So the evaporator is between process 0.4 and 0.1, or process 4 to 1. So the cooling rate, or the rate of cooling, is the mass flow rate multiplied by the enthalpy difference between 0.4 and 0.1, which is the enthalpy difference at the start and at the end of the evaporator. So we can use this function to multiply this by the difference between H1 and H4, where we find the cooling rate to be 6.609 kilowatts. For the COP, we can find this to be the cooling rate, or the cooling provided or being generated by the refrigeration cycle, divided by the amount of work that is being input into the system. Work input rate, in this case, in the form of power. So this is the cooling rate divided by the work input rate. But what is the work input rate? As we can see from this graph of the vapor compression refrigeration cycle, where we start from this point and isentopically compress up to this higher point. In this cycle, we find that the only temperature increasing process happens in the compressor, where isentropic compression occurs, and that is where the only work occurs. So the work input is only between 0.1 and 0.2, where the compression process happens, so that the same way as the cooling rate is to multiply the mass flow rate by the difference between the enthalpies of 2 and 1 to find the work input, and we divide these two values to get the COP of 2.263. For the minimum power, it is actually slightly relating to the exergy change over time in the evaporation or cooling process. So the formula is the cooling rate multiplied by the difference between the higher temperature and the lower temperature, which is 40, divided by the lower temperature, or the cooling temperature of the refrigeration cycle. And we get this minimum power to be 1.016 kilowatts to maintain the refrigeration cycle. For the reversible COP, it is used to find the second law efficiency. The second law efficiency we can find by using the COP actual cycle, which is the actual refrigeration cycle, divided by the COP if the cycle is 100% reversible or is considered a Carnot cycle. Since in this case we are considering the COP of a Carnot cycle, how do we find that? It is the lower temperature, the cooling temperature that we intend to have, divided by the difference between the temperature at the higher temperature reservoir and the lower temperature reservoir. And we find this to be 6.5 and the second law efficiency to be 0.348, or we can use the typical convention of the second law efficiency, or efficiency in general, being a percentage, and multiply this by 100 to get 34.817% for the second law efficiency. So as we can see here, by combining the RefProp program to find the values that we need faster, we can also use a spreadsheet to find the values that we want from the problem in a faster way as well. So the best part about using the spreadsheet is if our values change by using a different substance or a different situation, we can just change these values immediately, and the values for the problem will also change. And now, based on these values that we already have, by using the RefProp program as assistance, we can compare with the values that we get by calculating the problem by using conventional thermodynamic tables. So in the case of calculating manually, we usually start with our assumptions of the system being in a steady state and that kinetic and potential energy changes are negligible. And then we work with our diagram for vapor compression cycles, which usually look at like this. And in this case, we also consider that the problem tells us that the isentropic efficiency of the compressor is at 85%, so that the process of 1 to 2, which is the isentropic compression process, is not completely straight, but is actually slightly slanted to the right. But here we put the original number 2 point at the top is if it were completely isentropic, while the 2 prime is the actual cycle. So for the purpose of enthalpy and entropy, the point shown that is completely above in the compression process is the 2s, or the 2 in the completely isentropic position, while the 2 prime is the 2a, or 2 actual. So we start with the given values of 100 kilopascals at the start of the compression, which is P1, and using the tables for saturated refrigerant 134A, we find that the saturation temperature for 100 kilopascal of pressure is minus 26.4 C. The problem also tells us that the starting temperature for the compressor is superheated from the saturated temperature by 6.4 degrees Celsius, which puts it at a nice minus 20 degrees Celsius. Using these values of pressure and also temperature, we can use it in the same table to find the enthalpy and also the entropy of the fluid refrigerant 134A before it is starting to be compressed. And we are also given that the outlet temperature of the condenser, which is at 0.3, where it releases at a saturated liquid, is 39.4 Celsius. And using the same table, we find that the saturation pressure for 39.4 Celsius is 1000, or 1 megapascals. And we know for a fact that the pressure at 0.2 at the outlet of the compressor and the outlet of the condenser is the same, P2 equals P3. And also we can see from the graph that 0.2 and 0.1 is at the same entropy level. It is isentropic. So S2 and S1 is the same. And using these values of temperature and pressure, as well as the entropy, we can extrapolate from the tables that the enthalpy value at the process, or 0.2, is 289.14 kilojoules per kilogram. For the third process, we know that at the outlet of the condenser, the pressure is 1000 kilopascals, and it is at a saturated liquid state, where we can immediately find that the enthalpy of the fluid at that time is 107.34 kilojoules per kilogram, and the entropy is 0.39196 kilojoules per kilogram Kelvin. And for the fourth point, or the fourth process, the pressure is the same as the first one, where it is 100 kilopascals, and we know that the enthalpy of 0.4 and 0.3 is the same. Therefore, we can use that to find the entropy, which is 0.4368 kilojoules per kilogram Kelvin. And lastly, we need to find the actual values of the enthalpy and the entropy of process 2, not the isentropic value 1, where we can use the isentropic efficiency, which has the formula of H2, which is the actual, H2A minus H1 over H2S minus H1. And we can use this to find that the H2 actual is 291.7 kilojoules per kilogram. Therefore, we already have all our enthalpies and entropies for each process, and it's good to remind ourselves what each process or each point represents, where process 1 to 2 is the compressor, point 2 to 3 is the condenser, point 3 to 4 is the expansion valve or flash chamber, and point 4 to 1 is the evaporator. With all our variables ready, we can calculate the values that are being asked by the problem. The first of which is the cooling rate. The cooling rate is, as we know, for the refrigeration systems, the cooling happens in the evaporator. Therefore, it is at 0.4. And so we can predict that the cooling rate, or basically the heat transfer over time at the low temperatures, is the mass flow multiplied by the enthalpy difference of 0.1 and 0.4, which is the evaporation process, which is 0.05 times 239.52 minus 107.34, which we find to be 6.61 kilowatts. And now we can also find the COP of the refrigerator, which is basically the cooling process over the power input. And we can find it to be the cooling rate, as we found before, divided by the rate of work input provided to the refrigerator. The work happens in the temperature increasing process between 0.1 and 0.2, so it is the enthalpy difference of H2 minus H1 multiplied by the mass flow rate. And we can find the COP to be 2.264. Keep in mind that this is the actual refrigeration COP, not the ideal refrigeration COP. And so for the second part that we need to find, which is the minimum power input of the system. So here it slightly touches upon the concept of exergy, which is the exergy destroyed over time per mass heat flow in the refrigeration process is the minimum power needed to do the refrigeration in the system, which we can find to be the cooling rate multiplied by the difference between the ambient temperature minus the low temperature in the system over the lower temperature, which we can find to be 1.017 kilowatts. And lastly, to find the second law of efficiency of this refrigeration system, we can divide the COP actual over the COP reversible, or the ideal COP in a Carnot environment, which is the lower temperature over the high temperature minus the lower temperature. In this case, we can use the high temperature to be the way that the problem describes that the heat from the system is rejected to the ambient air at 27 degrees Celsius or 300 Kelvin. So the COP reversible is minus 13, which the problem states that the cooling is meant to maintain the state of the environment at minus 13 Celsius. So minus 13 over 27 minus 13 is resulting in 6.500, and we can find the quotient of the second law efficiency to be 37.8%. With these values, we can compare it to the result that we get using the relatively same formulas from the RefProp program. So reiterating the values that we get by calculating by hand back into this spreadsheet for easier comparison, we can immediately see that the largest difference occurs in the specific enthalpy and entropy values for each point in the cycle, where we can see that the values that we obtain from RefProp is significantly higher in terms of the enthalpy and the entropy compared to the value that we get from the table. And this likely occurs because in RefProp, it doesn't use the same assumptions of saturation and quality as it does in the tables. In the tables, we are assuming, especially in the specific points of H3 and in the specific points of H2, it is in a complete saturated vapor or saturated liquid form. And we are also assuming that there are no kinetic and potential energy changes, where it is likely that the RefProp values, which uses data from experimentation, to also consider these to be not the case, so that in this case, we find that there are some significant differences between the values that are obtained. However, despite these differences, the difference or the proportion of the difference between the enthalpies and the entropies of the values that we obtain from RefProp and the values that we obtain from the table are consistent, which in this case, as a result, the values that are obtained by the calculation of enthalpies from RefProp and enthalpies from the tables are relatively the same, where we find the cooling rate from RefProp is 6.609. The cooling rate from our calculation is basically the same as well. And it's same for the case for the work input, the COP, the minimum power, and the second law efficiency. For the COP reversible, of course, it'll be the same since it is only working with the temperature that is given from the problem. So here we can see the only difference between the n values by using RefProp and the n values by using calculation is that we can find these calculations at a higher resolution or a higher accuracy in a more faster way without having to look into the tables as much. So in this case, we can still find some advantages in using RefProp or other property reference programs for thermodynamic fluids to help with solving thermodynamic problems. And so in the future, in the case that we have a problem and we are able to use programs to help us solve the problem, RefProp is a good choice to find the enthalpy, entropy, and other values that are needed without having to work as much. So thank you, and I hope this video is helpful to show the advantages of using RefProp in comparison to calculating by hand.